All right, so what we're going to look at now is moving on to a third form of writing and displaying complex numbers. Okay, we've had rectangular or Cartesian form, okay, your a plus bi, and now polar form, where we have r times cos theta plus I sine theta, or sometimes abbreviated to r cheese theta, or however you pronounce it. But let's just stick with the full version for now. Now, how are we going to do this? The moving from Cartesian to polar form didn't require particularly advanced maths. Okay, it was some basic trigonometry, some SOHCAHTOA, kind of going over to unit circle concepts. But this one will require some much more advanced maths. Okay, now in geometric sequences, you saw that the limit of as you tend towards infinite terms of a sequence such as this here, okay, can be evaluated. Okay, we can say that this limit just equals 2. Okay, or we can essentially just say that this infinite sequence, infinite series, okay, sum of terms equals 2 if we were being a bit more lazy. Now that's a bit easy to sort of get your head around, given that these are just numbers being added up. Okay, but what if we extend this from just an infinite series totaling up to get you one number to a set of terms, okay, expressions in x, okay, where we have an infinite series of those that add up to a specific expression, okay, a specific function. Okay, what do I mean by that? Well, let's take a look. We are going to start off with e to the power of x. Okay, so instead of just adding up to 2, we are going to find a series of terms, an infinite series of terms that add up to e to the power of x. And again, we won't go into the complete workings of how this is found. That would require nearly all of calculus before you have a go at that. And well, if you are circling back to this at the end of your HL course, then maybe this will make a little bit more sense to you. But for now, you can just take my word for it that e to the power of x can be written as this infinite series here. Okay, you could test it even with e to the power of 1, okay, and see whether this does seem to be adding up to get you e to the power of 1. Okay, and e to the power of 1 is 2.71 roughly. And this sum, well, is going to be 1 plus 1, so that's 2, plus a half, so 2.5, plus a sixth, so 2.6 recurring, plus 1/24th, and we're starting to get very close to e at that point. So this seems to be working, okay, but it's not just for the power of 1, it's e to the power of x in general, okay, the whole expression, okay, with any x. Can be represented with this power series, you might call it, or Maclaurin series, eventually. Okay, well, that seems to be not particularly related to our polar form of complex numbers, so it's not clear why we've done that so far. Let's look at something that is more in line with what we've got above. Okay, so that's going to be cos of x. Okay, can we represent cos of x with one of these power series? And we can. Okay, cos of x is can be written with this series here. Okay, jumping by 2 on all these powers of x and alternating between plus and minus, and it will carry on like that infinitely. and to approximate cos of x. And well, you can guess we can do the same with sine of x. Okay, and well, you can see the pattern here quite easily, I'd imagine. We have odd powers of x and odd factorials, and well, that's related to the fact that sine is an odd function and cos is an even function. And so sine of x can be written as with that power series there. Okay, now clearly we have cos and sine in polar form. Let's combine them. Let's write this whole bracket as one power series. Okay, you can add power series in the obvious way that you'd imagine. Okay, you just add all the terms together. But I also would like to include this I here. So how's that going to work? Well, let's just change this power series. If I have I times sine of x, I would have I times this whole series, and so I would be multiplying every single term in the series. Okay, which would leave me with something that looked like that. Okay, everything just gets multiplied by I. Now we can add together cos of x plus I sine x. All right, and I'm going to alternate between the two power series because that way I'll have a nice increasing powers of x pattern. Okay, so what we see here is every other term has this I, because well, those are the terms that come from the sine power series. And also we don't have this really neat alternating plus and minus anymore. We have plus plus, minus minus, plus plus, minus minus, and so on. But that's fine. Now, where are we going with this? May not be clear so far. Well, we go back to where we started now with this e to the power of x power series. We see some major similarities between this fourth one that we did, this cos plus I sine power series, in that I now have just a perfect progression of increasing powers of x by 1 every time. But it isn't perfectly matching. Okay, I have these i's, and I also have these minuses on the third and fourth, on the sixth and seventh, seventh and eighth terms, and that's different than the power series I had at the top. Well, how are they related? Well, what we can see is if we evaluate the power series of e to the power of ix, okay, what I've written just below, we will start to see more similarities. Okay, so instead of x, I'm going to replace that with ix every time. Okay, I'm just going to write ix every time I used to have x. Okay, and this comes back to some of the basics of complex numbers here in figuring out what I to various powers is equal to. Okay, so ix, there's nothing we can do with that, that just equals ix. Okay, but these terms are now matching up. But do these terms match up? Let's see. Ix all squared is equal to I squared times x squared. Ix cubed is going to be I cubed times x cubed, and so on. So I could write them all like this, okay, but now this is where I need to decide what I to certain powers is equal to. I squared is equal to minus 1. Hopefully you know by now. Okay, so I can replace I squared with minus 1, and that will just change this whole term to a minus. I cubed is I squared times I, so I cubed is minus 1 times I, so minus I. Okay, so minus I. I to the power of 4 is I squared times I squared, so minus 1 squared, so 1. So that just almost disappears. And then I to the power of 5 is just I, because that's I to the power of 4 times I, and so on. And now finally I have exactly the same thing as I had in my cos plus I sine power series. Okay, effectively saying that cos of theta plus I sine theta equals e to the power of I theta. Okay, if we are to believe these power series will work properly. Okay, so I can say that r times cos theta plus I sine theta is equal to r times e to the power of I theta. Okay, so for example, if I now had a complex number that looks like this, then, well, this is just simply a complex number with a modulus of 2 and an argument of pi over 2. Okay, if I have this one here, let's say, and I wanted to draw it on the Argand diagram. Not very straight axes, but this is going to be pi over 3, which is about here, and this modulus will be 3, okay, and the angle will be pi over 3, okay, and one of the main benefits of this form of complex numbers, okay, which incidentally we can call Euler's form or also exponential form. One of the main benefits is, again, the multiplication and division of these are even more simple still than polar form and especially Cartesian form, because we can simply use our exponent rules, okay? And multiplying exponents, we use our addition rule, and for division we use our subtraction, and because of those rules, it is very simple and easy to use. Okay, and that is Euler's form.